5 minuten.
Stay.
Okay, I'd like to thank the organizers for the invitation, and I'd like to say happy birthday to Ron, but he's not here at the moment. Yeah. Okay, so the title is Categorical Formal Punctured Neighborhood of Infinity, and probably I'll first recall the geometric picture. Okay, happy birthday to Ron. So let X be a smooth algebraic variety over K, and let's assume that K has characteristic 0. Then we can take some, choose some smooth compactification, X bar. So X bar is smooth. This is an open embedding, and let's denote by D the complement. Actually, I don't require it to be a divisor. It can be, for example, 1 point or some, just some closed subset. And what I can take is the formal neighborhood of X bar along D. And what I'd like to do is throw away D and declare that this guy depends only on X, not on X bar. Intuitively it's clear, but I mean the problem is with this object is that for this one understand that it is formal scheme. This is a well-known notion. But I mean when you do such a punctured neighborhood, it's not a formal scheme. But what I'll be interested in essentially is in its category of perfect complexes, which is well defined. Namely, what I'd like to take is the category of perfect complexes on the punctured neighborhood, or just on the neighborhood of D, on the formal neighborhood, and localize it with respect to subcategory of perfect complexes supported on D. And this category supported on D is actually the same as perfect complexes on X supported on D. I mean, it's equivalent. And well, to be more precise, it will be algebraizable perfect complexes, but it's just a technical moment. And this quotient category is, by definition, the category of perfect complexes on the punctured neighborhood. Let's denote this guy actually by X hat infinity, so it depends only on X. And this is the category of perfect complexes on this punctured neighborhood of infinity. So it's some. So this guy is invariant of X. So some triangulated category. And actually, what I'm going to explain in my talk is that this invariant actually can be constructed starting from the category just dB of X, which is the same as perfect complexes on X because X is smooth. So we will have some abstract procedure which starts with a small dg category. And constructs some categorical formal punctured neighborhood of infinity, so that if we apply this construction to the derived category of X, we will get exactly this category of perfect complexes on the punctured neighborhood of X. What I'm going to, the construction which I'm going to introduce. And before I do this, I'll just just before I give the construction, I give an example of what we can get from it. For example, if X is a smooth, complete curve of K, then if we apply, actually you can apply this construction to DG categories, but to the DG algebras as well. So if we take just K of X, just rational functions, then after application of this construction, you will get Adels, the ring of Adels for X. And what I will also explain is that all kinds of reciprocity laws in this case, let's say reciprocity laws in K theory actually follow from categorical considerations, just in the complete generality. And this will actually resembles Tate's approach to residues. Okay, so
is there any way to limit an example? It seems like there would be a drastic difference between.
You're right. Of course, if you take a smooth projective surface, if you take the field of rational functions, you cannot get Adels because basically it's not a birational invariant. But still, I think that there should be some kind of higher analog of my construction, which should lead to this higher adelic residues. Following the approach of Williamson and other people.
Can you give any intuition about why, if you have a boundary that consists of some divisor and you blow out some intermediate section, why that does not change?
This is actually quite easy. Suppose that two kinds of complexifications, say X bar prime, is connected to another complexification by by single morphism. You get actually the morphism on these completions, and intuitively it's more or less clear that after you throw away this d prime and d, you get an isomorphism. Of course, you need to check this, but intuitively it's essentially clear. If you just blow up something at infinity, you get some divisor, but you throw it away. So, the result doesn't depend. Now, first what I want to recall is actually how the categorical approach to completion works. It's it's written in my paper 5 years ago. Let me give you a very simple example. Just take integers and take prime number. Then you can take the localization, just invert P, and take the quotient by Z, and take the homomorphisms over Z. Then what you get is just the periodic integers. This is quite an easy exercise, and because this guy is actually injective model, you can also write direct homomorphisms. So this is periodic integers. How this example generalize? It's the following. it can be generalized in the following way. Let's take some x. Let's say just some smooth scheme. So x will be smooth, and we have some closed subset z, and we have u is the complement of z. We have this open embedding, and let's denote it by g. And let's take E to be a generator of the category of X. I will usually write perfect complexes, but I mean for smooth, it's the same as the usual derived category of Coherent shifts. So let's pick some generator for simplicity, and let's take okay. We have derived category of quasi-coherent shifts on X, and we have a restriction functor to derived category of U, and we have the right adjoint, and also we have the derived category of quasi-coherent shifts supported on Z. We have an inclusion, and we have the right adjoint. This right adjoint is derived sheaf of sections supported on Z. And what the construction does is actually the following. We take just the derived sheaf of sections supported on Z, apply it to the generator, and take its the GeoGebra of endomorphisms. And actually, if you denote this by B, then perfect complexes over B give you the perfect complexes on the completion of X along Z. If you look at this example, when X is just a spectrum of integers, then this quotient is exactly if you shift it by -1, this will be exactly the derived sheaf of sections supported at the prime P. And after you take its endomorphisms, you get the completion. Maybe to be more precise, let's take this the usual exact triangle, which is actually induced by this semi-orthogonal exposition of derived category of X into derived category of U and derived category supported on Z. So we have this exact triangle, section supported on Z, goes to E, goes to G lower star, G upper star of E. Now, if we just take A to be, if we define A to be endomorphisms, direct endomorphisms of E, then let's denote by B. Okay, C. Let's denote by C the direct endomorphisms of the restriction of E to U. After identification of the derived category of X with the derived category of DG models over A, this exact triangle actually corresponds to the following. It's A goes to B, and here is B mod A shifted by -1. So again, here of course we can take the shift by -1, it doesn't change anything. This motivates actually the categorical construction of completion, namely, just let's give a definition. So let's F from A to B be a morphism of the GeoGebras, which is localization in the DG sense. This essentially means that the morphism of multiplication of B tensor B over A to B is an isomorphism in the derived category of bimodals over B. Then, just by definition, the completion of A, let's say along this morphism, I mean essentially along the kernel of the resulting functor of derived categories, is defined to be the GeoGebra of endomorphisms over A of B mod A. By B mod A, I mean the cone of the map from A to B. This gives you just a general construction of completion. We didn't yet pass to any complexifications. It's just non-commutative analog of completion of a scheme along a subscheme. Just a very easy construction in the abstract setting. Now I'd like to move to the punctured neighborhood, and I'd like to make this construction a little bit more precise. Namely, let us assume that we have. Let's assume that perfect complexes over B are obtained by localizing just by taking the quotient of perfect complexes on A by some subcategory S. Yeah.
Your notation RZ of E, is that like a sheet of sections?
Yes. Yes. Yeah, derived version. The derived functor of sections, yes. So we have, let's say we have some subcategory inside perfect complex on A, and we get such a short exact triple of categories. Then actually I claim that it is very easy to see that this S admits a full embedding into perfect complexes over this complete the GeoGebra A. That's essentially because I mean, if you take the short exact sequence on the large categories, on the whole derived categories, which are essentially int objects of these perfect complexes, then let's write int of S here, and this functor already admits right adjoint, and this under this right adjoint functor, actually A goes to B mod A shifted by -1.
So can you say what is B mod A?
B mod A is just by definition what I mean is cone of the natural morphism of A to B, considered as a morphism of right models over A.
Okay, it's Dijon.
No, I mean this guy is an object of derived category of A, and then I can take it to GeoGebra. Yes, that's what I mean. Yeah. This right adjoint functor maps A to B mod A shifted by -1. But I mean, if you apply it, if you restrict this right adjoint functor, say G, so we have G of A is B mod A shifted by -1, but G restricted to S is, let's write just identity. G acts by identity on S, and because S is generated by A, I mean all the objects from S are generated by A in the triangulated category. This means that actually we have such a full embedding. So S is a subcategory here. So in the geometric setting, once again, S is just the perfect complexes on X supported on Z. And it embeds into this perfect complexes on the completion of X along Z. Yeah, and as I said in the beginning, what we want to take is the quotient. So we want to take the quotient of this larger category by this subcategory. And this will be perfect complexes on the punctured neighborhood. Of course you can do it in such an abstract setting. So if you have some subcategory inside perfect complexes on A, you can apply this construction of completion, and you have embedding of categories, and you can take the quotient. I mean, this looks quite complicated. At least to compute or to prove some invariance under a choice of simplification. But let me give you a simpler construction of the same category, of the same quotient category, and it is very easy. Namely, again, let us take just an abstract DG localization morphism. Just recall that this means that B tensor B over A in the direct sense maps isomorphically to B by multiplication. Then what we need to take is actually the following. Let's take the category T. It will be a small subcategory inside the derived category of A, and it is actually generated by A plus B, just by a single object A plus B. Of course, it contains the full subcategory of perfect complexes over A, just because it contains A. Okay, and then just by definition, the formal punctured neighborhood of A along kernel of F, I mean the induced function from derived categories, is just the quotient of T by perfect complexes over A. Yeah, here again we don't take any complications. It's just the general story of how to define the formal punctured neighborhood. And again, in the geometric setting, we get exactly the usual formal punctured neighborhood. Now the main miracle that happens is that if A is smooth and proper, then actually the result depends only on B. That's what I'm now going to sketch. How to see this? So assume that in this picture A is smooth and proper. So we want to compute this quotient category, but of course, it is generated by the projection of B. So what we want to compute is the endomorphisms of B as an object of T quotient by perfect complexes over A. And let's look at it just as a bimodal over B, just before considering the algebra structure. So, of course, this is some DG algebra, but just consider it as a bimodal. Then, actually, by Dirichlet construction of a DG quotient, this guy is actually the following. We need to take the cone of B tensor over A. Yeah, from this moment I will not write derived, so home will mean our home always. So we take a home over A from B to A. And this tensor product goes to home over A from B to B. But because of our localization condition, so this guy is just B. Home over A from B to B is just B. So this of course doesn't depend on A, and it doesn't matter if A is smooth and proper or not. So now let's look at this guy. So let's take this tensor product of B over A, home over A from B to A. Let me recall you that we have this bimodal in the smooth and proper case. We have a bimodal which gives you an inverse of functor. So this bimodal is A shriek. It is basically okay, just home over A tensor A opposite from the diagonal bimodal to A tensor A. So it's like dual to the diagonal in this sense. So in the geometric case, it gives you, so if you have some smooth and proper varieties, then it gives you basically twisting by anti-canonical bundle shifted by minus dimension.
Why is there non-zero home from B to A?
Once again?
Why is home from B to A non-zero?
Well, at the moment, actually, I didn't plan this. I mean, you have some home. It's not. It's not a problem for me if something is zero. So let's take just this tensor product. So I introduce this inverse to self functor, and let's look more closely to this home which you are interested in. So home over A from B to A. Yeah, actually B is infinite dimensional, but still you can apply third duality if one of the objects one of the two objects is finite dimensional. So home over A from B to A is by third duality the same as home over A from A shriek. I consider A shriek as a right model here from A shriek to B star. That's the dual space over the basic field. And this guy, by the condition that this A is perfect because of smoothness, this is the same as A shriek tensor over A B star. Okay? Yeah, and now this tensor product rewrites as B tensor over A shriek tensor over A B star. But again, A shriek is a dual to the diagonal, and the diagonal is perfect. So we can rewrite this as home over A tensor A opposite from A to B tensor B star. Yeah.
Over the base.
Tensor. The tensor, yeah. Well, let's say by default, if I don't write over which ring, I mean over basic field. Yeah, and now let's apply a junction. This is the same as home over B tensor B opposite. So in bimodals over B, from B tensor B over A to B tensor B star. Yeah, maybe I should just make a comment that, very easy comment, that this B tensor B over A, this is of course the same as B tensor A over A tensor A B. So this means that this is a restriction of scalars of the diagonal bimodal over A. So we see that this is home over B tensor the opposite from B tensor B over A to B tensor B star, but by our condition of localization, B tensor B over A is just B. So we see that this is the same as home over B tensor the opposite from B to B tensor B star. And now you see that there is no A here. So it just depends on B. So we started with assumption that we have such a localization from something smooth and proper. We computed the result, and we see that it doesn't depend on A. Which means that we can actually forget about A. So if we forget about any smooth computation, just look at what happened to B. And also let's understand which kind of DG algebra we get, because so far we discussed only the biomodel. So we discussed the additive setting. So to see what happened, let's write once again this home over B tensor B opposite from B to B tensor B star. That's what we get for this tensor product. But now let us notice that if we do the same home from B to home over K from B to B, instead of taking B tensor B star, then this is just B. This is very easy to see. Already we see that if B is proper, then there is no difference. So they're just the same. Now it becomes almost clear what the definition should be. Namely, let us introduce the Kalkin. So the general notion: if V is a complex of vector spaces, say of K models, let denote the Kalkin algebra of V to be the quotient of the endomorphic DG algebra of V by V tensor V star. So by the operators of finite rank. So this is obviously a DG ideal inside this guy, so we can take the quotient. Now what we have here is the following picture. So we have a morphism from B tensor the opposite to this Kalkin algebra of B considered just as a vector space, as a complex of K models. So this morphism is basically left and right action of B on itself. I mean, of course, its quotient, it factors through the endomorphism of B over K. What we take is actually quotient cochains of the opposite with coefficients in this Kalkin DG algebra of B. And in such situation, this guy is a DG algebra. And B naturally maps to this DG algebra because, again, the actions of B and B opposite of this guy commute. So we have a natural morphism from B to here. So just by definition, so this guy is by definition the formal punctured neighborhood at infinity of B. From what I explained, it essentially follows that in the geometric case, this agrees with the geometric formal functionality. So how much time do I have? Okay, yes.
Sorry, that's Hoxie cochains, right?
Yes, this quotient cochains. It's R home from the diagonal bimodal over B to the Kalkin algebra. Yeah. So I explained that how this categorical formal punctured neighborhood is defined. And now let's look at some examples. Yeah, as I mentioned, if A is a rational function on X, where X is a curve, smooth complete, then the result will be the edges on X, ring of edels. This is one example, and another example is that if Y is proper scheme, but not smooth. And if you take the, I described the construction for DG algebras, but you can do DG categories as well. And if you take DG category of just the derived category of coherent shifts on Y, then what you get is just the category of singularities on Y. To be more precise, the opposite category to Y. And I just recall that category of singularities is a quotient of dB Koch by perfect complexes. Y. Yes, and this opposite actually arises because it's the same as the quotient of dB Koch by Schritt perfect. This is actually after you apply the Verdier duality. So this guy goes to this guy, so, and this quotient arises in this way.
If it was not the algebra but a G category, what would be the Kelvin category for B?
I didn't say that explicitly, but let's say that B is actually a diagonal bimodal, and if you work with bimodals, you can make sense. You can make sense of this in the framework of the G categories. I mean, it's just technical, quite easy. Okay, and so these are examples, and I'd like to.
What does it mean, Schritt perfect?
Probably I should write Schritt perfect. I mean, you just take home from, local home over OY from perfect complexes to the dualizing complex on Y. So that's Schritt perfect, and so this quotient is just a dual of the category of singularities. That's what we get. Probably it makes sense it's reasonable to give an alternative construction of the same category of the formal punctured neighborhood, which looks quite surprising. Namely, let's take vect infinity to be complexes of K models where just the dimension of the cohomology is bound, so this is such V, such the dimension of cohomology of V is bounded by some cardinal which is such to large. So the only reason to take this cardinal is to get a small category. Otherwise you encounter such difficulties. And so for our DG category B, let's take the tensor product of B with this infinite dimensional vector spaces, and we have let's take perfect complexes over this, and we have actually two natural fully faithful functors from B to this category. So let's know them by iota and Y. Y stands for Ioneda. Actually, iota is basically just a tensoring by K. I mean, K is an object of this category of infinite dimensional vector spaces, and you just tensor by K. And the second functor Y, it actually starts with B. It goes by Ioneda to functors, DG functors from B opposite to vector infinity. This is well defined if the cardinal is such a logic. And this goes to, well, let's assume that B is smooth. Then this goes to perfect complexes over B tensor infinite dimensional vector spaces, because as it is well known that a DG functor gives you a bimodal, and bimodals is the right way of looking at functors. And so we have this two functors, and actually we can take the full subcategory of the perfect complexes over B tensor vect infinity, just generated by the images. So just generated by the image of iota and image of Y. Then you actually get semi-orthogonal decomposition. Yeah, so both these guys are fully faithful. So iota and Y are fully faithful. You get a semi-orthogonal decomposition. So you get this perfect complexes on the punctured neighborhood of infinity, and the image of iota. This is the first one, and if you apply the mutation, you get another semi-orthogonal decomposition. This is image of the Ioneda, and this perfect complexes on the punctured neighborhood of infinity. So this looks quite wild construction, but I mean it gives exactly.
So it coincides with the second orthogonal.
I mean orthogonal to the image of iota is the same as the right orthogonal is the same as the left orthogonal to image of Ioneda. And if the category is proper, then these two functors are actually the same. So there is no orthogonal.
In general, they would be like the right and left adjoint to something, but something does not exist. So,
Once again?
in general, they would be the right and the left adjoint to something,
Yes.
but the something.
Something is zero. It's just. What do you mean not exist?
No, but can you recover iota, describe iota and y both as a right is going to be left adjoint to something?
Yeah. So you're right. Yeah, you're right. Yeah, actually we have actually a DG functor from B to here, and this is actually extension of scalars, and you can show that this is a co-induction, the right adjoint to restriction. Yeah, you're right. Yes, let me mention how this construction gives you the reciprocity laws for curves, which will be very similar to Tate's approach, but I mean it appears just very naturally in this framework. Namely, you have so from this construction it follows that you have also this embedding of perfect complexes on the punctured neighborhood of infinity into functors from the opposite, actually to Kalkin infinity, where Kalkin is just the quotient DG category of infinite dimensional vector spaces by finite dimensional. and this gives you okay, you have this probably I'd like to write a commutative diagram. You have this embedding, but also you have perfect complexes over B, which goes here. And the point is that it factors through functors from the opposite to vector infinity. And it follows that you always get a map from K-theory of a formal punctured neighborhood of infinity of B, tensor K-theory of the opposite, which goes to actually K-theory of K shifted by 1, because the K-theory of Calkin category is just identified with K-theory of the basic field of shifted by 1, because K-theory of infinite dimensional vector spaces is 0, as is well known. The point is that if you compose this with the map from K-theory of B tensor K-theory of the opposite, then the composition is 0. Basically because it factors through infinite dimensional vector spaces. So this is the general story, and if you let's now apply it to the case of rational functions on a smooth complete curve. Then in particular, let's just know that K0 of rational functions is of course integers, and we get a natural map from K-theory of adults to K-theory, K dot minus 1 of the basic field. And this is basically the sum over all the local residues. This map is actually, so we have a residue from the K-theory of the local field to K-theory to the K-theory of the residue field, and then we have the norm to the shifted K-theory of the basic field, and this is actually just summing up over all the points, and basically the reciprocity states that if you compose this with the map from the K-theory of the rational functions, then the composition will be 0. So this includes Weyl reciprocity, Cantu-Carré reciprocity, and you can also apply this to Cauchy homology, and you get the residue theorem. So actually, you can apply this to all edited invariants of the categories, and this recovers the corresponding reciprocity laws. In this non-commutative framework, this statement is just an easy consequence of the vanishing of additive invariance of infinite dimensional vector spaces, which is actually Tate discovered this in 1960. This idea was discovered by Tate in 1968. So from this point of view, this is actually how you see this in the DG categorical framework. Probably do you have some time? Okay. Then I'll probably mention just a couple of natural properties of this general construction, namely. Again, in the geometric case, you have this restriction functor from perfect complexes over X to perfect complexes on the punctured neighborhood of infinity. And of course, the kernel of F is the perfect complexes with proper support. Yeah, and now if we consider the abstract categorical setting, then it's well known to experts what are the perfect complexes with proper support. And these are actually the G models with fine dimensional homology. And it is not hard to check, so it's a proposition that the kernel of this extension of scalars functor from perfect complexes over B to perfect complex over B at infinity is naturally identified with, they're usually called pseudo-perfect models. These are models with, let's say that B is a DD algebra, then the assumption is that just homology of M is fine dimensional. And another property is that if again in the geometric setting, if you have a morphism from X to Y, so they both are smooth, and the morphism is proper, then it actually gives you a morphism on the formal punctured neighborhood. And you get somehow this commutative diagram. And this is again the special case of the general categorical picture is that if you have a DG functor, from this morphism we have the inverse image functor in the other direction, and in the general picture, if you have DG functor which admits a left adjoint, to be more precise, extension of scalars has left adjoint. This is, in the geometric case, this existence of left adjoint is equivalent to S being proper. Then you get such partial functoriality, so you get this commutative diagram. So A goes to B, goes to A hat infinity, goes to B hat infinity. So it is in this aspect. This works in the general setting. And probably I mentioned just the hope. I think it should work as it was mentioned in the beginning, that there should be higher anodes of this construction, which in particular would give rise to this higher adelic residues in the approach of Berenson, generalizing the data approach, that there should be probably something like n-fold construction, and this should probably be related to the considering multiplying not just by a single copy of infinite dimensional vector spaces, but by n copies, and considering certain functors between these guys, some cubical diagram, but at the moment, so let's say this is just a naive guess. So there is no, I don't have an understanding of this picture. So, but I think it should work. And another hope is that logarithmic Dirac complex. Let's say mixed complex. Mixed complex starting from the derived category of X. I mean, the generalizing the Cauchy-Rosenberg theorem. I mean, we know that Cauchy homology corresponds to differential forms, and probably this considerations with punctured neighborhood of infinity can lead to the logarithmic version. In particular, there should be a general degeneration conjecture for the slope-Durand complex, and probably this will give a much better understanding of the whole picture. Okay, so I stop.
Questions? Comments? Yes. Just one more comment and a question. There is a series of works by Brownling, Gruchenik, and Woodson. And I think they were categorical construction of higher dimensional edges as well.
High dimensional edges, yeah, but I mean,
n-state objects, which you're familiar with.
but I mean, high dimensional analogs. I mean, the Benetton construction is also given in my paper 5 years ago. But I mean, not in that way, which I would like to obtain. I mean, I have so we always had this localization of the categories, but after we introduced the completion, it turns out that if you take the drive category and it takes the filtration by the support, if you just apply this localization, completion, and so on, you get automatically get the Benetton construction of edges. Yeah, but this is not exactly what I want to have. It doesn't. This is a cute observation, but it doesn't give you, for example, reciprocity laws in P theory or something. So yeah, it should be understood better what happens.
What's the last full motivation of the rest?
You mean this motivation for this in particular? In particular, yeah. I mean my construction. If B is proper, then probably I should have written this. Then so this implies that this guy is 0, right? And roughly what I want to have is that suppose that we succeeded in this n-fold constructions, and then if x inside x bar, and suppose that x bar minus x is d is a smooth divisor. Then what should happen is that if we apply this two-fold construction to perfect complexes, then it should be 0. What should happen? Should have such a vanishing. So intuitively it's like it, but I don't know exactly how it happens.
And conversely. Well.
Probably converse. Okay.
There was some questions.